there you have it. So first of all, I put the lecture of the first, the screencast of the first lecture online, so you can see that. And I put in a separate module here, where all the screencasts are going to be. At first, I thought it would be a good idea to have all the screencasts with the modules where they were actually being talked about, but I instead made a separate one, so you'll find all the way at the top of the Canvas website, I think the second module or so is one that's called screencast, where all the screencasts will in the end up. Then I put the data as far as we have it online. I think we have now 150 or 160 or so submissions complete, and we're still lacking a few, but I put the ones that I have online already, so that you can look at the data that we have. And what I also put online is separate reading guides per module. So for each and every module you can now see which chapter of the book it is supposed to cover, including which parts of the chapter that you need to go through, so that if you want to work ahead, that will also give you some pointers as to where to go. And the other thing that, that I should perhaps mention is that what we had is a bit of talk about what the wikis should look like. A couple of people actually started filling out these wikis, and one thing that was sort of annoying is that if you have the actual assignments and the answers sort of taking turns, so assignment, answer, assignment, answer, assignment, answer, it gets a mess pretty fast. So instead what I now did was for the first wiki I sort of brushed up visually what's going on there, and I put the assignments all the way at the top, making it clearer that you should mess with the assignments and write the answer beneath it, where beneath it you should write your answer in terms of a do file. So the stuff that is the actual answer should be runnable in Stata, and you add comments, using the stars and the double slashes and so on. If you look at the first wiki, you'll see what I mean. I didn't look at the actual content there, but I did make sure that the stuff that is now written there as an answer is runnable in Stata by and of itself, and that would actually be useful. Okay, so all that will work itself out online, I hope. Back to what we're up to today. First, the general aim again. This is what we're supposed to be doing in the end. You get some data, you think about what to do there, and then in the end you figure out what's in the data about the world. And before we get there, we need sort of a run-up that will help you understand the different statistical tests as we're going to get. Okay, so all this we had already, Stata and the tutorial on Canvas, and it's all about how two sets of variables are related or are not related. And we need a little bit about the general logic behind hypothesis testing. This is not in any of the chapters explicitly, so this is sort of assumed between the lines or between the chapters that you more or less know what that is. And what I'll try to do is hammer down that point a little bit more today. And I think the only occasion where you're going to hear this is right here. And in the book, it's more or less assumed that you look at another statistics book somewhere to try to figure out what's going on. Luckily, let's say one lecture is enough to get you through the ideas here, I hope at least. Okay, so this is the main aim of today. The whole talk is meant to do exactly this. What should happen is that whenever you see any kind of statistical test, doesn't matter what it is, that first of all you don't panic and you know what to do, and what to do is relatively easy. We'll go through the separate steps that you need to figure out. And the good part of the way in which we do it is that, let's say, the real statistics are not really necessary. You have to be able to understand statistical tests as they are presented to you, but not so much all the technical details that lie behind it. So that's the aim of today, to get you through that. Okay, just to mention this, normally I'm not going to repeat anything that I talked about last time, but I just want to make clear that for some of the output that I'm going to show here, this is all output that I realized through Stata commands, and I assume that, let's say, the easier Stata command you should cover already by now. A tab and the summary and the description and the codebook and the generate command or a graph, all that stuff, I assume that you either know it or are willing to figure it out on the go. All of this is actually mentioned in the wiki of the previous time, so this shouldn't come as a big surprise. And this is a typical example. This is something that we can get from this data. This is an overview of age. It says tag age on the top left. You get for each and every age how many cases you have in the data. DES, or describe, gives you an overview of the data set in general. Summarize gives you a summary of a variable, or a summary of all the variables, even if you want to. And if you ask for specific details, you can get them as well. So all this is stuff that you're going to see in the next couple of slides, and all of that is standard output of Stata, including graphs. This is, I think, the one most used. The histogram gives me an overview of this variable. This is what the age variable looks like. In fact, this is what it looked like in the data of last year, but it doesn't matter so much at this point. A box plot you can get through graph box, and a scatter plot below here you can get through the scatter. Okay. All of that is in chapter 5 of the book. Yeah.
Should you always put y first and then x in the scatter plot?
If you want to have y on the y-axis and x on the x-axis, yes. Okay. Yes. No. Okay, so, yeah, something else that I wanted to mention, because I'm going to go through it in some detail later, is that we have stuff here in the detailed summary of a variable. So this is a variable that's called sucker score, doesn't matter what it is. Here you see additional stuff that you learn about this variable. The mean here, well, we knew that already, because that you get from the basic command as it is. But you also get here the median, 50% of the cases is smaller than this value, and 50% is larger than this value. And what you could also get, but not immediately, is what's called the mode. That is the score that occurs most often. So if this would be the actual soccer score that you have here, and you simply look at the frequency table and see, well, where's highest number 40, so apparently 5, that's the one that occurs most often, and this is why 5 is the mode. So all these things that you could be interested about actual variables in your data, you can find in these standard Stata commands. Okay, that was all a run-up of the output that you're going to see in the next slide. But this is the aim of today. So let's see. Okay, first, the big thing is that normally we have samples and not the whole population. So we're interested in something about a whole population, and it's too much work, too much time, too much money to somehow measure the whole population. So we're going to measure only a sample of the whole population. And that makes matters complicated. If we would simply be able to measure everything, then everything would be easy. Then we only have calculations. And the word for that is statistical inference. So this is our population. All students at the university, or every person in the Netherlands, or what have you. We can measure only part of that. That part is called a sample. And we want to know something about the population, which is sort of problematic because this is only a small part of the population. And we need to sort of blow up that what we find in the small sample to learn something, hopefully, about what the population is like. That's called an inference, trying to figure out what the population is like based on the sample. Yeah, then, okay, the sample stuff, all that you do there is relatively easy. You know, you have the data, and you simply look at means or differences or all the stuff that is relatively easy mathematically. In the sample, we can check, if the average grade that boys have larger than the average grade that girls have. You know, just add them all up, and you divide by how many you have. That's easy for the sample, but you want to know something about the population, and this is where the nastiness comes in. So all the stuff that you're about to hear about statistics and probabilities and distributions and who knows what, all that is about the fact that we have to go from the sample to the population. In the sample, everything is easy. Okay, this is the standard example that I use here, taken from the Dutch television program Keuringsdienst van Waarde, where they found out that in many materials in a supermarket, especially in pizzas, there is something in there that is called analog cheese, where analog cheese is actually no cheese at all. If you would have a block of analog cheese, then it looks like a cheese, whitish, but in fact there is no cheese in there at all. There are only two things in there, palm oil and starch. And it's really cheap. So you can buy a block like this, it costs you close to nothing. So what they do on a pizza is they grate that stuff all over it, and they grate a little bit of real cheese, because that's expensive, and then they put on the packaging, well, what's in there is palm oil and starch that's in there anyway, even if there wouldn't be any cheese at all on top, so they don't lie. And there's cheese, not that much, but there is cheese. And then they make you think that all the stuff that's lying on top of the pizza is actually cheese as well, so which is sort of cheating. And in fact, for some of the pizzas, if I remember correctly, they found that there hardly was any cheese in there. So basically what you're tasting is the idea of cheese and not so much actual cheese that is on the pizza. So what they did was they took a sample, 11 products from a supermarket where, well, let's say analog cheese might be in there, and they found that 5 out of 11, or 45% actually, contained analog cheese, so fake stuff, so to speak. Okay, so that's 45%, and now we need something, well, it's normally called a 95% confidence interval. I'll talk in more detail about what that means in a minute. But we need to say something about, okay, 45% in this supermarket, but we need to have an estimate of, in general, what is that percentage, roughly. And there, you can choose between, well, A, B, C, D, and E. What do you think? We have 11 of these products sampled, then what are we able to say about the actual percentage of products that we have that contain analog cheese? So think for yourself for a minute if you think this is A, B, C, D, or E, what might it be? Anybody who knows how to calculate this? Might happen. Perhaps it would be last year. Okay. Sorry, I won't do that. Okay, so think for yourself what you think the answer might be. The answer actually is 50 to 75%. So with 11 cases, 11 things sampled at random from the supermarket, you end up in D. And the way to get there is, well, if you look at something like this, where the thing you're interested in is a proportion, then if you want to know how far to the left and how far to the right you should look, so to speak, for an interval like this, then you can think about the 1 over square root n rule. Here, n is 11, so the square root of n is 3 and a bit, so this is about 1/3, 30%, and indeed 45 minus 30, 45 plus 30 is indeed that D answer. So that 1 over square root n rule, its rule of thumb is not exact, that will give you already a crude estimate of how large the variation in the population might be, given that you have sampled only 11. Of course, if you want to be more precise here, this rule will give you how many that you will actually need. So if you want to be able to say something of the kind, okay, it might be 45%, but given that, I want to be able to say that it is between 40 and 50, then that difference should be 5 percentage points. So this should be 1 over 20, and we need n equal to 400. So with n equal to 400, we should be able to reduce that interval to something that is way smaller. If you want to get it really, really small, 45% plus or minus 1, then this has to be 1%, this has to be 100 over here, and you have to have 10,000. So if you want to be really precise, you need quite a lot. You have to sample 10,000 products from a supermarket. Might not even be doable because perhaps there aren't so many. And we saw this same thing actually in the survey that I put online. Here I had a question where I said the Dutch Road Assistance Club is checking out how many car workshops correctly repair the cars that are being offered. They sampled 25 and they find that 10 out of 25 did not correctly repair the car, so 40%. Again, same question, what is a reasonable guess here for that 95% confidence interval? I didn't want to use that word in the actual question, but here you can do the same thing. 1 over square root n here, 1 over square root 25, 1 over 5 is 0.2, or 20 percentage points. So if I have an estimate of 40% with a sample of 25, I can say something like, well, that's 20 percentage points to the left and 20 percentage points to the right, to give you an idea. And here you see what you answered. So the right answer is this one, number 2. 30% of you had that correct, and, well, many of you also didn't have that correct. Yes?
why doesn't it matter how many of something there is? So there would be 20 pizzas in the country and 20 different and 2 million cars. Why does that matter?
I have to think if I have the slide in today's slide list, but we're going to get to that in detail why that is. And it doesn't. Sort of. By the way, that 1 over square root n, that's a rule of thumb, so that you can do on top of your head whenever you see something like this. However, you can also do it exactly if you want in data. If you type CII proportions, and then 25 sampled, out of which 10 ones, so to speak, where they found something. The CII stands for confidence interval immediate, and then you get it and you see that it's not so bad actually, that 1 over square root n rule here. 21% to 61%, that's actually what the interval is supposed to be. Okay, back to the logic of statistical hypothesis testing. Once more, because I cannot bring that home too many times, 2, perhaps 3 kinds of variables that we're interested in. Categorical ones with 2, that's a special class, dummy variables, and categorical ones with more than 2 categories. And interval variables, the ones in between you won't use so often. These 2 you have to be able to take into account, know which is which, and know which different kinds of statistical inferences belong to these kinds of categories. So let's see. Okay. So first, just to show you that in principle we have these kind of things in the data. One way to go through the data would be look at males and females and look at what they answer about how far below or above average people think they are, and then compare these 2 variables. And simply look at, okay, this distribution over here that I now have for everybody in the data, is it any different for boys versus girls? Okay, so we have 5 categories here, I have 2 categories there, could make a 2 by 5 table and calculate if there is a difference, and that thing is called a chi-square test. We'll go through that in more detail. Here you see what the actual analysis looks like. So this is sort of looking ahead to what we're going to do in some more detail. The only thing that is of interest here is that in the end, here you get way at the bottom, you actually see it in detail, you get 2 numbers. One that is a statistic that says something about the comparison being made, and one is a conclusion. And that's the big message for today, that in the end, for each and every test, you'll get 2 outputs. One is statistic on which the eventual conclusion is based, and the other one is the actual conclusion. So the rest is basically, well, not optional, but less important, so to speak. You have to be able to see that these 2 numbers are always there. Here another example. Do boys give higher estimates than girls in terms of what they expect in terms of their net income when they are 35? Now this is different. We had 2 categorical variables in the previous slide. Now we're looking at boy-girl, that's categorical, versus interval. You now need a t-test. You get a lot of output. The main thing to focus on is here again, you get something where you get a number and an actual conclusion over there. You get a couple more numbers, so it's slightly more complicated. But in the end, always at the bottom of the test, there is a number that will give you the conclusion. Same thing here. Now I have 2 interval variables. I'm looking here at age and net income. Are students who are older more likely to report higher income or lower income? Again, now you get only a single number as an output. Doesn't matter if it's actually that one. Coincidentally, also here the one at the bottom. But in the end, for each and every test, you get a single number at the bottom, and the main thing is to understand what that number is representing. Oh, I'm missing a picture. So here you see these same things once again. The only thing I want to emphasize here is, in the end, after you have done the test, you get an actual number. That number is the answer to the question that was raised. So we're not doing anything about the details of these tests here. The only thing is trying to figure out how does this work, and it always works in the same way. In the end, a number. Easy. 2 other things that are slightly more complicated. We also have in the end multiple regression. We're trying to predict the estimates of net income based on some other characteristics. There it's a bit more complicated because the output contains way more numbers, and then you have to know where to look. the same things that we saw on the previous slides are now in this column. We'll go through all of that in more detail. And this one is something totally different altogether, but still, in the end, gives you a number that is representing the actual test. Okay, I know I'm flying through the actual tests here. I'm not talking about the content at all. The only thing is, at the end, a number. Okay, and that'll help. Okay, now, empirical distributions. Let's suppose that we could measure everybody in the population as, for instance, the CBS does. This is a distribution of what people in the Netherlands earned, I should say, in 2012. So these are incomes simply counted for everybody, and we can do this because everybody pays taxes. And then we can come up with a distribution like this. Now, you can think about, of course, if this would be too much information, all these data points, you might try to convey to somebody else what this looks like. You could say something like, well, the middle is about there, and it's sort of leaning towards the left. That might be a useful suggestion. It's running between, well, let's say close to 0 and somewhere over there, which is 100,000 plus. And, you know, that at least could give you a rough idea of what is going on there. But in any case, if you would have all this, then calculations on this kind of stuff would be relatively easy. I have to check there. Yeah, you could make different measures of how wide this thing is. You could say just the minimum and the maximum. That's the easiest. However, the minimum, you know, 0 or even -6, usually these are sort of weird cases, and the maximum is also sort of weird. So you might say, let's chop off 5% here and chop off 5% there. These are the weird ones. So, you know, the bulk is in between these two. Might also be of use. And in any case, if we do it, as soon as we have that, we can simply calculate it because we have all the data here at our disposal. Okay, so everything we would want to calculate with an actual empirical distribution about the whole population would work. We have all the data that we need, and we can run, let's say, simple arithmetic on the data. Okay, that we don't have. We can do the arithmetic, but only on the sample. And that makes it a bit more complicated. So what we could do is try to figure out, well, if we only have the sample and not the whole population, maybe at least we could look at characteristics of that sample itself, and then hope that if the sample is decent, that the characteristics of the sample at least say something about the actual characteristics of the empirical distribution as a whole. So if I look at the sample and I say, yeah, the middle is about here, that might be quite a decent approximation of the middle of the true distribution. Or saying like, well, the minimum and the maximum is about there. That again might be a decent approximation of the data in the true distribution. Okay, let's see what we have here. Yeah, these were the ones I think. Yeah, this is from our own actual data. So from the 150 or so that we have now. So I asked you, give me an estimate of what you think you will earn in terms of net income at age 35. That was measured in different categories. So the categories, you see a histogram of those over there. Ran from 1 to 16. And the 1 to 16 was actually corresponding to different intervals. So I think one was, I don't know, nothing to 1,000 or so. And here what I did was I used data to recalculate the categories to actual net values, and then look at the summary statistics here. So your net income estimate at 35 years, well, the mean is 4,200 euros, which is a substantial amount. So I value the optimism in the group for sure. You know, to make something like this in net benefit, you have to have a decent job, and it might work, of course, really good. One of the things that is a bit problematic with that mean is that it is quite sensitive to somebody who has a really high estimate, and there were one or two who either actually believed or just gave a random answer and said, I'm going to earn quite a lot, so way on the edge of the distribution, and that could seriously influence that one. So this one is actually a bit better in the sense that it is way less sensitive to outliers. So the percentile is at 3750, which is also quite decent. Okay, so let's hope that that will actually happen. This to get rid of. Yeah, a couple of more of these empirical distributions. The only thing that I wanted to show here is you can make graphs, of course, with each and every one of these. Yes?
Just quickly on the first slide, in your code, you saw that you had like repeated the line, but then just changed the numbers.
There.
Like that. And it's also possible to just program a loop, so you don't have to type in all the numbers again. Or is that not possible instead?
Yeah, of course, looping is, for loop is totally possible. In this case, it doesn't help so much because you have to type the numbers here in anyhow, but that for sure is possible. So something where you run over the numbers 1 through 16, but at least you don't have to type this part is certainly possible. Okay, these empirical distributions, the only reason why I showed just a couple here is that if you happen to know any theoretical distributions, you will easily see that normally they don't fit with any of those. So it would be nice if there would be a Poisson distribution obviously in there for something else that we know quite well. A normal distribution perhaps, we'll talk about that in a minute. But all these kind of things you typically do see. So if you look at your sample and you hope for, let's say, something smooth, it's typically not there. So that's also a bit of a bummer, because if we would have that, then we could see, this has a sort of, and something that we know, a known distribution. Might very well be that our empirical distribution for the whole population also has that characteristic, but that typically doesn't happen. So let's see. If I want to convey something about what the data looks like, the standard way to do this would be to go through a couple moves. The first move would be, where's the middle? And we have to define, okay, what is a decent middle? And we're used to using the mean, and there's a good reason for that we'll see later. But of course, you could have all kinds of other ideas about that. For instance, the median that we looked at before, in a way is better because it's way less sensitive to outliers, so that should work actually way better than the mean, but we don't do it. Or you could say, well, we look at something halfway, so we take the maximum and the minimum, we subtract that, and then we go sit right in the middle of these two, which is again a different number. Well, we sort of got used to using that mean, so even when we look at these kind of things, because our males or females taller, then we're totally accustomed to understanding that as, it's not that we need that are all males taller than all females, but just the average value of height that we measure there. It is good to realize, though, that there are a couple of exceptions where we typically don't when we compare groups. When we look at means, anybody know of an example where we don't do this? You want to compare two groups, or two persons, or two, doesn't matter what, and now I don't look at the, on average, who's better, or who's taller, any idea? When does it happen? Typically. No? Yes?
The qualitative data, maybe? Or when you need a chi-square test?
Give me an example of the qualitative data. I don't see what that might be.
When you cannot say that something is better or bigger. Or...
Yeah, of course. Yeah, if we don't have data that allow bigger or better or smaller, then there is nothing. Then the mean doesn't make any sense. So then for sure we are not taking the mean. I was looking for something in another direction actually. Whenever there's a contest, then typically we also do not look at the mean. We look at which country plays soccer better, the Dutch or the Germans. It's not that we average out across the group, and the average German is slightly better than the average Dutch person. No, we look at the best one and compare those. So there we look at the extreme of the distribution, trying to compare if the extremes from one group are better than the extremes from another. We're not really used to thinking about this in these kind of ways because we're so accustomed to contest. You send your best ones and that's typically it. But very often for statistics, we typically don't do this. You look at these means, and that's pretty much what we'll do. Okay, so the midpoint of a distribution, that would be a mean. That was the same one. Yeah. Second thing. Now, if you want something for the shape of a distribution, we have something for that too. not that much, but two things we can work with. One is what's called skewness, and that is the extent to which a distribution is leaning towards the right or the left. And I normally forget myself which is which, but the weird way to remember it would be if the distribution is sort of leaning towards your left, then it's skewed to the right, which is not very easy to remember, but you know, that's how it is. So the way in which the hump is leaning, that is not the way in which the skewness is working. So that is a measure that you can actually calculate. I'll give you the definition in a minute. Something that looks like this, so perfectly symmetric. The hump is in the middle, has a skewness of 0, and depending on which way you are leaning, the skewness is positive or negative. So one way to talk to somebody else without giving the actual distribution is, well, this is something that is sort of leaning towards the left or towards the right. And something else is called kurtosis, like this. I'm not sure if that's an English word, but let's say the peakiness of a distribution. To what extent is there a peak? And I have to check what these words are like, because, you know, if they are, let's say, very peaky, which is that one, this is called leptokurtic. I'm not going to ask that at any kind of exam. I don't think there's a real reason to remember it. But there are words for very peaky and not so peaky, and the other one is platykurtic. Okay, must be Greek. So that's something else that we can try to say about the actual distribution, and taken together, and I actually forgot one. Where is the midpoint of a distribution? The second one that I forgot to talk about is how wide is it? Is it varying a lot to that direction and that? Is it leaning towards the left or the right? And how peaky is it? That together is something that we can measure in a sample, and that is something of which we can hope, if we measure those characteristics, might be quite decent approximations for the empirical distribution as a whole. Okay, here you see them a bit bigger, and if you want to memorize the actual platykurtic and leptokurtic, feel free. Mesokurtic, that's in the middle. And one other thing to realize is that where here the obvious midpoint is at a skewness of 0, there the kurtosis stuff is in the middle at kurtosis equal to 3. And this is because, because of this. Here you see the actual mathematical formulas that you need for, well, the mean, we know that. The variance, how hard stuff is varying around the mean, or the standard deviation, both measures of how wide the thing is. Then the skewness is defined in terms of these moments, symmetry and peakiness, and because they are defined like this, that midpoint for kurtosis is not exactly at 0, but it is at 3. Okay. Empirical distributions, a couple of characteristics that we can use about these distributions. Now let's get to work, because now what we can do is, well, this is the list of numbers in the data. That's just my spreadsheet, easy enough. This is a summary of the spreadsheet in terms of a picture, a histogram, and I could try to tune that down even more to, okay, let's forget about the details. Let's only look at the mean, the variance, how wide it is spreading, the kurtosis, and I even forgot the skewness, of course. Okay, so that'll help for empirical distribution. Set that aside, now we go to theoretical distribution. Okay, the standard example for theoretical distributions and how to work with them is the coin flip. So we're flipping a coin, we're wondering about is this a fair coin, yes or no, and this should in principle all be relatively familiar to all of you. I need to go through this at least once. Nowadays, we don't have to calculate this by hand at all. For instance, Wolfram Alpha will do the actual mathematics for you. So what you could look at here is for 50 tosses of a coin, what do we get it then? Well, lots of things here. This is the effective number of heads is 25. Well, we could have thought of that before. And here you see the distribution that you could expect for the number of heads. So for 50 flips, you'll get 25 most of the time, but you might get 24 or 23 or 22 or 30 or who knows what, and there you see how often that will occur. So there, for the theoretical distribution of flipping a coin, we know how to calculate, and we know what will happen if we do this lots and lots of times. One other one that is perhaps even more famous than that coin flip is the standard normal distribution. This you must have seen before, this hump or the bell curve. If you, well, you perhaps didn't know that, but there is an actual formula that produces this graph over here, and you see this normal distribution time and time again in statistics. And the reasons for that will become obvious a couple of slides down the line. On this one, we can just as well calculate as on that coin flip example. Given that we have this formula, if somebody would ask, what is the probability that if the 0 is here in the middle, that we end up way over there at 3, then I can do the calculation and see, well, that's 99.1%. That is to the left of that number, and a little bit only to the right. Yes? No. No, the point is not so much that we're trying to memorize these formulas. The point is here way more, there is a formula for this. So if you want to do calculations on this, it's doable. Okay? There is no uncertainty about nothing, and we can run our calculations. And the other thing that's interesting about this one is that there are two parameters in here, that mu over there, and that sigma. And with these two, it's completely defined, that normal distribution. The mu says where the midpoint is, so in this case mu is equal to 0. And the sigma says how wide that hump is, and it is a measure of this distance. So that's sort of helpful in the sense that the 4 that we thought we might need, the midpoint, how wide, skewness and kurtosis, we can forget about the skewness and kurtosis here because 2 is enough for this normal distribution. Okay, again, if you want to do calculation on this we can do. There is a whole gallery here, not stuff that we are going to use in detail, but there are many, many more, let's say, known distributions that we typically look at. Not sure which ones you have seen before. Uniform should be relatively well known. Everything is equally likely, so if you throw a die, you have 6 sides, and each of the 6 sides is equally likely to show up. That's easy. But there are certainly something that you've not seen before, for instance, I think Birnbaum-Sanders distribution that you typically do not hear before very often, or a beta distribution, perhaps also not so likely. All of these have given formulas and allow you to run your calculations relatively easily without uncertainty in them. Okay, so now what we would hope is, it would be nice if we have a sample and any of these distributions looks sort of like what we have here. That would be nice if we can do our calculations. Okay, yeah, so that's the big point. If we have that theoretical distribution, that would be fine too. We have our formula, not necessarily memorized, somewhere on paper. If somebody asks, okay, tell me how many people are between this and this, you can do the actual numbers, and we're all good to go. Okay, now we're sort of running into trouble because we have two ways out of the problem that we have. First, it would be nice if we have the empirical distribution of the whole population. We don't have it, then we could do calculations. Or it would be nice to have a theoretical distribution that we see matches our sample. Would also be nice, and we also don't have that because all the empirical distributions that we do have do not. Okay, I'm going to go through an example that I hope you know, because the general idea of this is way more important and stretches beyond the actual example. This is why I would like to refer to an example that you hopefully know how to deal with. Although I'm not even so sure that these kind of things have been covered. So this is where you think about, if I flip a coin lots of times, can I then figure out if the coin is fair? That used to be high school stuff. Anybody who hasn't seen these kind of things before, just admit it. If not, would be fine. Sort of. Okay, if I get a sort of there, there might be more who don't dare to admit it. Okay, so the issue is not so much the actual example, the issue is the stuff that lies behind all this. So let's see how this goes. This is the prototypical thing to do. We have a coin here, we do not know if it's fair, and what we do is we flip it 1,000 times to try to figure out if it is. And the general logic is, of course, sort of obvious. We count the number of heads after we flip 1,000 times, and if we come up with a number that is sort of weird, then we think, yeah, this is probably not a fair coin. Okay, no heads at all, yeah, really unlikely, so very likely that it is not a fair coin. By the way, on the slide you can read it, but if you look at the slide by yourself, you can see here that the actual graph here was generated in Stata itself, so if you're interested in how to program this stuff, you can have a look at that. Here you see that I did this lots of times, so I flipped the coin 1,000 times, and then I counted the number of heads, and then I stored, and then I did that 10,000 times. So here you see a distribution of 10,000 times 1,000 flips of a fair coin. I write the number of heads here in the graph, and you see that most of the time we end up around 500, which would be expected. It might happen that we end up over there for 50. It's totally unlikely that we end up over there or that we end up over there. And the aim is, of course, we have to figure out if we get a given number, for instance here 525, if we do it once, then when does this start to be weird? And we have to think about what it means that we get a weird number here. And there is a standard way to do it that we sort of decided among researchers. Okay, we look at the 5% weird cases that we have, so 2.5% on that side, 2.5% on that side. And if your number ends up there, then we say, okay, it's not very likely that the hypothesis that you started with, that the coin is fair, is actually really the case. So we can do the calculations to see, okay, 2.5%, where is that? So we might have the line somewhere where there's only 2.5% over there, and 2.5% over there. We can do that by simulation, as I did it here, or by calculation. If you use Wolfram Alpha, they will calculate this actually for you. But we could try to figure out where the weird numbers start. Okay, that by and of itself is nothing new. The only thing that we need to realize here is that, well, first of all, that I said 2.5% to the left and to the right. This is just something that we all agree upon. We could use something else as well, but that standard alpha equal to 5% value is typically what we normally use here. And it's just something that people agree upon, and that's it. The other thing that you need to realize from the example here is that we have in the beginning something that we typically call H0, a baseline hypothesis, and the baseline hypothesis must include an equality. In this case, it was the coin is fair, probability of heads equals the probability of tails equals 0.5. The reason is if we don't have an equality there, then we cannot generate a graph like this. If I start from the coin is fair, let's see what would happen then. Then I can generate this graph. If I start from, the coin is not fair, but I do not know what it is, then I cannot generate this graph at all. I have to assume something about that coin that is enough to work with. So we need an equality there equal to 0.5, equal to 0.4, fine by me as well, but you need something to work with at that point. And then we need an alpha that we normally stick to 5%, where we say, okay, if we end up in the weird part of the distribution, all the way to the left or all the way to the right, then we say, okay, forget H0. H0 is rejected. If H0 would be true, we in all likelihood wouldn't end up there. Okay, that's all standard how hypothesis testing works. Now let's see, what do we have here? Yeah, the nasty bit about this is that in a way as a statement it doesn't say so much. It would be nice if we now would know a lot more, but we don't know so much. The only thing that we have here, well, we started with H0, that was, okay, 50% heads, 50% tails, and that's it. And now we find, well, it is one of two things. Either that it is rejected, that H0, or it is supported, or actually you should say not rejected. And the first thing to realize about this is you're not allowed to use any other words than these. So anything that looks like it but not is completely the same, don't do it. So there is no H0 is not true, or H1 or the alternative hypothesis is true, none of that. So there are only these kinds of terminology that you can use. The hypothesis is rejected or supported, and that's it. You wanted to? No? Okay, then, well, let's see. Why do we get into this trouble? It's not so easy to really say H0 is now true. Because, well, we could look at different kinds of H0s that we could have started with, and that would also have worked. For instance, let's suppose that you flip a coin 1,000 times and you have 511, just a random number of heads there. Then what you would find is H0 will be supported. if you look at the probability of heads equal to 0.5. Okay, now you would like to conclude, but then H0 must be true. But that doesn't work so well, because if I use another H0 here, for instance that one, probability of heads is 0.51, so it's close but not exactly the same. That one would also be supported. So I can generate lots and lots of H0s here that would all be supported by a number of 511 out of 1,000. So this already suggests that it's not very likely that if you do it this way, you start from an H0 and then you get rejected or supported, that you then immediately know something about whether that actual H0 is the true one, because there are many others that could work as well. And this is actually how a 95% confidence interval is defined. If we test at that alpha equal to 5%, then a 95% confidence interval is actually that set of H0 values that would all be supported. Okay, so we get H0 is first 0.5, we do our calculations, we do our coin flips and so on, and then we end up with a confidence interval, and that confidence interval represents, okay, all the H0s here that would have been supported given that we do something as we do here, the flipping of the coin. By the way, in Stata you could get this immediately as well, again through confidence interval immediate proportions, 1,000 flips, 511 are heads, and then you get the exact confidence interval ranging from 48% to 54. So here, that means all the values that you can think of that lie in that interval between 48% and 54. If you would start with that as an H0, these would be supported as well. Okay, so one other way to look at these confidence intervals, because they are quite sure to lead to all kinds of nastiness in terms of interpretation. So there are two ways to interpret these that at least we know is correct, and it's tough to grasp. Because in principle, we did all this to say something about the fairness of that coin, and preferably to say something about what is the likelihood that you get heads here, if it's not 0.5. But that's typically not how it works. So the first one in green here, that is the confidence interval interpretation that I already mentioned on the previous slide. So you look at the whole set that is inside the confidence interval. If H0 would be using one of these values, fine, that would be supported. That we have already. The other one is slightly more complicated. And it is, well, if we repeat this whole procedure, so that coin flipping, and then we count the number of heads, and then we generate a confidence interval, then we would expect that if we do that lots and lots of time, in 95% of the cases, the confidence interval that we create should include the actual value in the population. So if the true value would be 0.5, and if we do this lots and lots of times, this kind of procedure, what we expect is in 95% of the confidence interval that we create, we find that 0.5 is indeed in there. So basically, the confidence interval says something about confidence intervals, not so much about the actual values here. And all the things that you would like to say here are really not true. And here you see an example of what is typically not true. So you would like to say something like, yeah, there is a 95% probability that the true value is within that interval. In a way, that's the most natural way to think about it, but that's wrong. So that will for sure lead to quite a lot of misunderstandings in the future. We'll talk about this in more detail, in fact, in the third methods course, trying to figure out what are the kinds of intuitive statements that we can make about this. But this one is not one of them. So never interpret that 95% confidence interval as, it's 95% likely that the true value is in there. Tough luck. Let's see. Oh, we had that already. Okay, so let's recap, because now we're getting to where I want to go actually, and that is that all statistical tests are basically of this kind. Okay, first we start with some hypothesis about what the world is like, and that hypothesis must involve an equality, something that we can calculate with. If you don't have this, there's nothing to do. Here, coin is fair, probability of heads is 0.5. Or probability of heads is 0.6, would also be good to work with, because it's an equality. Then we look at the data that we have. In this example, 525 out of 1,000 flips were heads, and we get an estimate, and that estimate says something about the likelihood of this. So 520, that number, that 525, that says something about whether H0 will be supported. And you can see that here simply by, well, if the number would have been 999, you for sure would think, well, H0 is not likely to be correct here. Then, yeah, we look at, okay, if we would do this lots and lots of times, what would the distribution look like? Well, here it looks like this. You see the same picture now in the small. We did this by simulation. You could have calculated this as well. We look at the far end to the left, 2.5%, the far end to the right, 2.5%, and we decide, okay, it's either in that region on the outskirts, or it is in the middle. If it's in the middle, we say H0 is supported. If it's on the outside, we say it's rejected. And we look at 5% simply because it's something that we agreed about. Okay, so this is simply what we did here, and the good news about this is, well, in principle, all statistical tests work like this. I have to peek at what my next slide is. Yeah, because this principle, in fact, is general for all tests. So if you would know what H0 was for any kind of test, then in the end, if you could interpret the number that you end up with, that would also help to interpret the test, without doing all the actual statistics. Let's see how that goes. Okay, any test runs like this. First, a hypothesis about the world. Boys score equally high on their estimated future income than girls. Let's say the correlation between age and the estimated net income is 0.25. Also has an equality, something that I can work with. Then we look at the data, and in the data we calculate a statistic that says something about how likely it is that that is actually true. If that would be true, what would then happen? Can we come up with a statistic that says something about whether or not this is likely? We look at what the distribution is, as we did for the coin flipping example, and then we simply check, okay, that value that we came up with here, is that in the far end, or is it in the middle part? If it's in the middle part supported, in the far end it's rejected. Okay, let's see how that goes in practice, because that will actually help quite a bit. Yeah, first, doesn't look so good just yet, because that coin flipping example was easy. There we know how to do the mathematics, and there, if not, I could perhaps simulate this. But in our sample data, I basically know nothing. I can say something about what's in my sample, but I know not exactly what's going on there. And what is going to save us here? It looks like that we're sort of out of luck. We need something like a theoretical coin flip to work with, and it will turn out to be not the case. And our savior here, I'm going to skip this. Our savior here is what's called the central limit theorem. This is what's going to do all the work for us, and this is also what causes that we look at the mean all the time, and not to something else. Okay, central limit theorem, I'll show it in, let's say, in glorious mathematical detail, and in a little bit more easy to understand natural language. It's not exactly the same in this case. Looks like this. The top part is let's say, the true mathematical wording of the whole thing. If we have a set of n independent random variates, and each of these sets have an arbitrary probability distribution with a given mean and some variance, then x norm blah blah has a limiting cumulative distribution function which approaches a normal distribution. Yeah, it's really hard to understand what that means. So look at the stuff here in the red. Let's say the loosely defined central limit theorem. The mean of a large enough sample from an arbitrary distribution typically has something close to a normal distribution. So if I do something, I collect from an empirical distribution that has any kind of shape, doesn't matter, something that is in our data. I collect something from that, I take the mean of that, and that thing will have a normal distribution. And that's good news, because we can work with the normal distribution and calculate on it. And that will solve actually the problem. So I have to check if I have that here. That thing that we use in that coin flipping example, and that we didn't think so much about, in a way this is also weird, because we started with coin flipping, where you have 50% heads, 50% tails. If you then look at these means, you get something that looks like this, and this resembles, doesn't it, a normal distribution, and this is not a coincidence. And the strong statement of the central limit theorem is, doesn't matter what you start with. If you take a sample that is big enough, and you look at the distribution of a sample like this, when you are interested in the mean of that group, then you'll get a normal distribution. Yay, this is a good thing. So indeed, that the bell shape that you saw in that coin example, this is not a coincidence. You could have started with anything and then do the same thing. Okay, I sample 1,000, and I look at what happens. I calculate the mean. I look at all these means and I put them in a histogram. Doesn't matter where you start, you end up with something that is bell-shaped. Central limit theorem is making sure of that. In fact, the proof of the central limit theorem, if you Google a little bit, you'll find that there are many proofs. Many are really, really long. This is the only one that I could find that was relatively short and would fit on a single slide. And don't worry, this is not something that we'll ask at the exam. But just to show you here, this is not trivial stuff. You have to do some serious math here to make sure that it actually works. Yeah.
So you take multiple samples, and from every sample the mean, and then from these multiple means, they are normally distributed.
Yes, the distribution of that set of means has a shape like that. As in the coin flipping example where we did the same thing. Okay, so again, no need to be able to derive this yourself, but just to show you that the math behind it is not standard stuff. I think here, is this even complete? Yeah, I think it is. So here you see that in the end, if sample sizes are large enough, then you should get close to normal. Okay, that is our savior. Okay, here once again, you can see it, but it's not perfect. There are all kinds of holes in there that don't work so well. So that would be better if we use more samples, and also better if we use larger samples. But still, the good news is this means that as long as we're interested in means of groups, that's actually fine, because then we can calculate using these normal distributions. And that will work in our advantage. Here too, this is the example that I skipped a couple slides ago. But for instance here, this is a distribution that I see for girls, where we ask to what extent do you like classical music? And here, same thing for boys, to what extent do you like classical music? You might be interested in, let's say, the average value that girls give here is that higher than the average value that boys give there. What you can do is you can sample from this and sample from that and look at how the distributions in the end should compare. And what helps there is if you look at the mean of this, again, even though this is not normal just yet, these means themselves will look nicely normal. This is also why we, of course, look at the means. All this will work. Okay, so we're sort of in a bad spot. At least it looked like we're in a bad spot, but in the end, it turns out that we're doing quite well, because the mean of an arbitrary variable with an arbitrary shape approaches something that looks normal, and that's good. Okay, we're sailing away from the abyss and should be good to go. Okay, now how that will help. And that's the almost the final bit that I'd like to mention here. Okay, back to the stuff that I went through in the beginning. Let's look at what we have here. We have these different kinds of tests: the chi-square test, the t-test, and a correlation where we do an actual test. And for all of these, if you want to understand what's happening here, the only thing that you need first is, well, there must have been, given that there is a statistical test, an H0 somewhere in the beginning, a baseline idea about what the world will be like. Well, what would that be here? Here we see males and females cross that with, would you consider yourself to be better than the average student in your class? Well, you see here that we have 68 boys and 35 girls in this example. Now, there are different kinds of H0s you could think about, but as soon as you figure out what it is relatively obvious here. We're looking for an equality. Well, if there wouldn't be any dependence between the rows and the columns right here, then you would, for instance, think if I have, let's say, 70% versus 30% over there, then I expect that I have 70% versus 30% over here, and over there, and over there, and over there. If If that would be the case, then apparently it doesn't matter so much if you're a boy or a girl, but that distribution is the same everywhere. So here we think H0, a likely candidate would be the distribution across these rows and columns is the same as we have here at the end. And that indeed is the H0 that is being tested. And in the end, also we get a conclusion about whether or not this is true. And that's the number over there. But let's start from the H0. That is what H0 here is. It's even easier for the second one. There we have a t-test. So we're comparing boys and girls on whether or not there is a difference in terms of the net income that they expect for themselves. H0 is always, there is no difference, or there is equality of some kind. H0 is going to be, well, boys and girls score the same number here. So the mean for boys equals the mean for girls. That's the H0 that we're going to test. You can already see that in this sample, this is not exactly true. Females score 7, and in this case, males 7.5. You could wonder about whether this difference is big enough to be of interest, but in any case, the H0 that we're using here is no difference between boys and girls. There should be equality. Same thing there. This is correlation between two variables. Age is interval scaled. Net income is also interval scaled. The standard baseline hypothesis would be, let's assume that there is no relationship between the two whatsoever. So knowing one doesn't help you in predicting the other. That's the H0 that you need in this one. I think I have it on the slide here too. And that'll help you interpret what's going on, even if you don't know exactly what the actual test is doing behind the scenes. Yeah, then. Second bit is, okay, number one is if you, let's say, are approached by a new statistical test, try to figure out what H0 is. Number two is, make sure that you know where to look for the actual conclusion. Okay, so here, for the chi-square test, we get a number there that is related to that alpha value of 5% that I talked about previously. So we're trying to figure out if H0 is true there, then how likely would it be that we get the data that we have? And if it is really unlikely, for instance, a number here that says 0.00001, then we're going to reject H0. It's totally unlikely that we get something like this. Here it's not so bad, apparently. 0.75, certainly not in that range far away. That range far away is below 5%. So here we would say, okay, H0 is supported. There are no differences across the columns and the rows here. Same thing here. Do that again. First thing, you have to know where to look. It's actually there. We look at if it would be the case that H0 is true, so boys and girls give more or less the same net income estimate, then let's see how likely it would be that we have the data that we have. Well, totally likely, a 48% here, which is, well, good or bad, which is at least way above 0.05. So here again, we would support H0. There is no evidence here that boys and girls are making a difference here, even though that number is not exactly the same, 7.5. Here, the same thing. If it would be the case that age and net income are totally unrelated, then how likely would it be that we have the data that we have? Well, not unlikely. Would be unlikely if you would have a really, really small number. So as long as you have a number there that is above 0.05, you support H0. And this sort of reduces the interpretation of any kind of statistical test to two things. First, knowing what H0 is, what is being tested here. And second, knowing where to look for, let's say, the definitive answer to that. And that is here, there, and there. And in these cases, the conclusion is the same everywhere. Because these numbers are larger than 0.05, we support H0. Okay, yeah. And that is the nice part of this. For all the tests that we're going to see, and we're going to see many, not only for the actual test that we're going to do that I already mentioned, the chi-square, the t-test, but all these tests themselves have assumptions. These assumptions themselves can be tested, so for that we need another statistical test. All these statistical tests have the same format. You start with H0, you have to know what that is. Usually that is the easiest idea about what the world looks like. The correlation is 0, this one is equal to that, and then you have to know where to look for the answer, where usually this is called a p-value. If it's below 0.05, we reject H0. If it's above 0.05, we support H0. And then of course you could ask, yeah, what do we do when it is 0.05? Yeah, then we don't know exactly. We're sort of halfway. Okay, yeah, I can see that, especially because, you know, it took a long time before I got there, but in the end we sort of reached what I wanted to reach, because this is helpful. You might have dozed off a little bit and may not see anymore why this is a good thing. This will help us interpret any kind of statistical test without doing the actual statistics ourselves. Let's see why. Okay, first, all the data that we're going to encounter are samples. We never have the whole population, and that is in principle a bad thing, because that causes that we need to work to know something about the actual population. As long as you do your calculation on the sample itself, there is no probability or statistics involved. That's all measured stuff. You can calculate your mean, your standard deviation, your minimum, your maximum. That's just arithmetic, not complicated. Okay, the probability stuff comes in, and the distribution things, and the left part and the right part, all that more complicated stuff, only when we want to infer something about the population. So that is what makes us work. Okay, then the different tests that we're going to do on the data that we have totally depend on which kinds of variables that we are comparing. Categorical versus interval, and a combination of these, so two categoricals together, categorical with interval, or two interval variables, that causes which test that you need, and that is simply something that you have to learn and know by heart, which test goes for what. Then if you encounter a test, you'll see that this is always the same. It first defines an H0, that one you have to know, and even if you don't know it, then every once in a while you can try to figure it out from what is in the output. By the way, sometimes Stata gives H0 even in the output. Then, the good news is, what you should do, what typically Stata will do for you, is check the sample and see if it has produced something that is weird, given that H0 is actually true. That is simply the execution of the test. Stata will do it for you. And you get a number back, where you, if that number is below 0.05, you reject your H0. That's it. And besides the rejection of H0 or being supported, you do get confidence intervals depending on the actual test that you do, where you have to know what these confidence intervals represent. And it is a set of values for which H0 is supported. Be wary there that you do not conclude what you would like to conclude, something like the 95% probability that the true value is in there. Forget it. That's not what it actually is. Okay, the fact that all this works, and the fact that we typically use means to compare different kinds of groups, this is all due to the central limit theorem that somebody else has so nicely proven for us. So that all this works is because of this, otherwise we would be in trouble. And it also means if you at some point get all these tests mixed up in your head, and you might, the key thing to do would be to think back, what is the H0 that we're testing here? And if you know what that is, then the rest is relatively easy, even without knowing the actual statistics that will go on behind the scenes. Okay, before I move to this, any questions about this part? Because the only reason that I talk about all this is because it helps us for the coming chapters in the book. And in the book it will be more or less assumed that all this is known, or that some statistics course is explaining this to you. Any questions about how this is supposed to work? Yes?
Why do you choose to reject or accept
What would be, so the question is, why do we talk about H0 all the time and not so much about the alternative hypothesis? And the answer is basically the only one of the two where we can say something about is the one where we have an equality, the thing that we're using to figure out if we get weird data or not. H0 has, yeah, it's equal to 0.5, it's equal to 1.5, this one is equal to that. We can try to figure out what the distribution should look like in the end, and then see if we have weird outcomes. The alternative hypothesis is typically defined as not H0. So H1 would be, yeah, the probability of heads. It's not 0.5. Yeah, then I can never conclude if my data is weird, if the only thing that I know is, yeah, it's not 0.5. This is why we talk about H0 all the time, and it's problematic because, yeah, you would like to have something more in detail than just, yeah, 0.5 is supported, and even that is not clear exactly what that means.